Chapter 2 in your textbook has lots of great stories. If any part of our textbook is really a history textbook or a storytelling textbook, it's Chapter 2. So what it does is it starts to tell the history of the atom, and that is going to be fundamental to everything we're studying in chemistry, obviously, because chemistry is the study of, the materials, life around us, so the atom is very important. So let's start out first by just thinking about back in the old days what some of the initial thoughts were on chemistry. So before it was even named chemistry, we had alchemy, which really helped us figure out what is the scientific method, because they were trying to get gold. Very often science is pushed by the desire to get rich, and alchemy was no exception. Alchemy was the desire to take any substance and turn it into gold. You can see why that would be profitable business, but it didn't work, obviously, and we now know why today. But the processes that they took, the procedures, how they laid out, even lab notebooks, if you will, that was all started thanks to alchemy. And so with alchemy now we have the revolution of science is just going to take off from there. And so we have ideas and concepts such as the idea that all of the earth, all of matter can be one of four elements. So you've got air, fire, earth, or water. And obviously we know now that it's not those four subcategories, but everybody firmly believed that. And so we have to get away from those four things. And so we first started doing that with Sir Robert Doyle. And so he was the one that really pushed the idea that there are these things called elements, and that as we learn more about each element type, we can add to our list, our repertoire of knowledge, and help us understand what all these elements are. Because if we understand that they're different, we can then understand why they're different, how they're different, what makes them that way, and then how we can use them for, the betterment of society. The first law I want to talk about is the law of conservation of mass. The idea that mass can't be created nor destroyed, only really changed in form. And so the idea is if you start out with 5 grams of mass, you should end up with 5 grams of mass. That mass may have changed forms, 100 times between the beginning and the end of an experiment, but it's still, start with 5. You end up with 5. You can't just destroy it. And a lot of people thought that you would destroy mass, because if you destroy it, some of it left as gas, and they wouldn't see gas. And so they would assume that they lost material. But thanks to Antoine Lavoisier, we are able to know that, in fact, we don't ever destroy matter. We still have the beginning and the end are still the same amount. And so Antoine Lavoisier was a French chemist and also an accountant, which was a great way to pay the bills unless it's the French Revolution. And the French Revolution, that is a time where you're considered to be part of the aristocracy, and sorry, but he was really good at, paying attention to the little things. And so it's those little things that allowed him to really notice that even the smallest masses, he could collect them, such as gases. And so he realized that mass wasn't getting created nor destroyed, it was just changing in form. But it was his meticulous note-taking ability that he had perfected through accounting that really turned him into a fantastic chemist and makes it so we remember him today. And that is who this law of conservation of mass was really created by. Inspired by Antoine Lavoisier, we now have Joseph Proust. Joseph Proust developed what's called Proust's law. It's also called the law of definite proportions. And the idea is that if you have the same material, it's always going to exist with the same proportion of each of its components. So like water, we know that's dihydrogen monoxide. There's a great website called The Dangers of Dihydrogen Monoxide. You should go look at it. It's all about how, there's this horrible chemical that causes all of this drownings and other things, and it's water. And it's really funny because it tells you all the dangers of water. And if you just read it, you'd be like, we need to ban this horrible chemical. But then you find out it's water. But long story short, we know dihydrogen, 2 hydrogens, monoxide, 1 oxygen. Water is always in the ratio of 2 hydrogens to 1 oxygen. If it's not in that ratio, it's a different compound. And so he was the one that established that anytime you have a compound of material, you're always going to have definite proportions that are going to explain the ratio of the two. The next law that we want to talk about is the law of multiple proportions. And this was developed by an Englishman named John Dalton. He noticed that if you take all of the masses and you can somehow slowly distill them down to whole numbers, so meaning water is H2O, it's not H4O2. You always want to distill it down to the smallest number that you can for that compound. Now, could there still be another compound that needs to have higher numbers? Absolutely. But the idea that John Dalton proposed is that there is some multiple proportions that you can always distill a number down to. So for instance, if we look at carbon monoxide versus carbon dioxide is C, 1 carbon to 1 oxygen. Carbon dioxide is 1 1 carbon to 2 oxygens. And so these are the lowest common multiples. And so between these two, we're able to notice that they are different entities and they can distill to the smallest number. And so basically the idea, if you've got more than that, then you probably have more than that atoms, which you probably have more than that atoms anyway. We'll talk about that later. So these laws that we just talked about, the law of multiple proportion, law of definite proportion, led Guy Lussac and Avogadro to develop new theories, and that theory was one of diatomic molecules. Diatomic molecule simply means dia, two molecules, so two molecules combined together. So what they did was they were looking at these reactions right here, or very similar ones, where they took and they noticed that hydrogen plus oxygen, one amount of each of them, yielded 2 amounts of water. Then hydrogen, one of them, plus 1 chlorine yields 2 amounts of hydrochloric. And these ratios didn't quite seem right to them, because if you've got 2 plus 1 and it yields 2, why would 1 plus 1 yield 2 as well? Shouldn't this yield 3? And so the only way they did to come up with and explain these was there must be something that's happening at the atomic level. And what they noticed is that hydrogen gas, it doesn't just combine by itself with one hydrogen single atom by itself. It exists diatomically, meaning there's 2 hydrogens anytime you have a molecule. There's 2 atoms of hydrogen linked together. Same for oxygen, same for chlorine. And if you did that, they made these molecules, these equations become balanced. So what I mean by that is this 2 is a coefficient, and it tells you how many molecules you have in the chemical reaction. This 2 that's underneath the hydrogen, that tells you that there's 2 atoms of hydrogen combined together. So now if we have 2 molecules plus 1 molecule, now does it equal this? Here I've got 2 of my hydrogens. Here we have 2 of my hydrogens, but there's 2 hydrogens, and so that means I have 4 hydrogen atoms on this side, and I have 4 on this side. And then oxygen, I have 2 oxygens, and on this one I have 1 oxygen in a molecule, but I have 2 molecules, so I have 2 oxygens. So they just noticed that they were balanced, and similarly for this bottom one. So the big concept from this is that they were able to figure out that every single reaction relied sometimes on there being the presence of atoms bound together into groups of 2. And so what you'll see on the screen now is the list of diatomic molecules. I remember that there's 7 of them. So at room temperature, 7 molecules will exist naturally as a gas in a diatomic fashion. And so those are noted here. So you'll notice that these on the screen, they form like a 7 on the periodic table, and then we have hydrogen all the way over there all by itself. And so you should be prepared to remember which of these are diatomic. So if I were you, I'd pull out your periodic table and highlight these 7, because anytime I say a hydrogen and oxygen, they combine together, you're going to assume it's a diatomic molecule, not oxygen by itself. But altogether, these founding fathers of chemistry, if you will, really laid the principles that we will use almost daily in chemistry.